Nuclear species, also known as nuclides, are atoms with specific numbers of protons and neutrons in their nucleus. These nuclides can be stable or unstable, depending on their atomic structure and the forces that hold their nucleus together. The study of nuclear species is a fundamental aspect of nuclear physics, and it plays a crucial role in many fields, including energy production, medicine, and environmental science. One of the defining features of nuclear species is their atomic number, which is equal to the number of protons in the nucleus. This value determines the element to which the nuclide belongs, and it governs many of the atom's chemical properties. However, the atomic number alone does not determine the nuclide's stability or reactivity. Instead, it is the balance of protons and neutrons that determines the nuclide's nuclear properties. In general, nuclides with a balanced number of protons and neutrons tend to be stable. However, as the number of protons or neutrons deviates from this balance, the nuclide becomes increasingly unstable. Unstable nuclides can undergo radioactive decay, which involves the emission of particles or electromagnetic radiation from the nucleus in an attempt to achieve a more stable configuration. The rate of radioactive decay is governed by the half-life of the nuclide, which is the time it takes for half of a given sample of the nuclide to decay. There are several types of radioactive decay, including alpha decay, beta decay, and gamma decay. Alpha decay involves the emission of an alpha particle, which is a helium nucleus consisting of 2 protons and 2 neutrons. Beta decay involves the emission of either an electron or a positron, depending on whether the nuclide is neutron-rich or proton-rich. Gamma decay involves the emission of gamma radiation, which is a high-energy form of electromagnetic radiation. The study of nuclear species has important applications in many areas of science and technology. In nuclear power plants, for example, nuclear species are used to generate electricity by harnessing the energy released during nuclear fission. In medical applications, nuclear species are used for diagnostic imaging and cancer treatment. In environmental science, nuclear species can be used to study the movement of pollutants and contaminants in soil and water. In conclusion, nuclear species are atoms with specific numbers of protons and neutrons in their nucleus. These nuclides can be stable or unstable, and they can undergo radioactive decay in an attempt to achieve a more stable configuration. The study of nuclear species has important applications in many areas of science and technology, and it continues to be an active area of research and exploration. The discovery and study of nuclear species can be traced back to the late 19th and early 20th centuries, when scientists began to explore the structure of the atom. In 1896, French physicist Henri Becquerel discovered that certain materials emitted radiation that could pass through solid objects. This discovery led to the study of radioactive decay and the development of radiation detectors. In 1898, Marie and Pierre Curie discovered 2 new elements, polonium and radium, which were highly radioactive. They also coined the term radioactivity to describe the phenomenon of unstable atomic nuclei emitting radiation. The study of radioactivity led to the discovery of many new nuclear species, including isotopes of existing elements and new elements altogether. One of the key tools used to study nuclear species is the mass spectrometer, which was first developed in the 1910s. Mass spectrometry allows scientists to determine the mass-to-charge ratio of ions, including atomic nuclei, and to identify the isotopes present in a sample. This technique has been instrumental in the discovery and characterization of many nuclear species. In the early 20th century, Ernest Rutherford and his colleagues conducted a series of experiments in which they bombarded atoms with alpha particles. They observed that some of the alpha particles were deflected, indicating that the atom had a small, positively charged nucleus at its center. This discovery led to the development of the modern model of the atom, which features a nucleus surrounded by a cloud of electrons. In the 1930s and 1940s, nuclear physicists began to study the behavior of atomic nuclei more closely, including their structure and stability. One of the key discoveries during this time was the concept of the neutron, which was first proposed by James Chadwick in 1932. Neutrons are uncharged particles that reside in the nucleus of an atom, and they play a crucial role in nuclear stability and radioactive decay. During World War II, the study of nuclear physics took on added urgency with the development of the atomic bomb. Physicists such as Enrico Fermi and Robert Oppenheimer led the Manhattan Project, which developed the first nuclear weapons. After the war, nuclear physics continued to be an active area of research, with new discoveries and technologies emerging in areas such as nuclear energy, medical imaging, and environmental science. Today, the study of nuclear species remains a vibrant and active field of research, with scientists exploring new ways to understand the behavior and properties of atomic nuclei. Modern tools such as particle accelerators and nuclear reactors have allowed researchers to study nuclear reactions and decay processes in unprecedented detail, opening up new avenues for discovery and innovation. The names of members of nuclear species are determined by the number of protons in their nucleus, which corresponds to the element to which they belong. For example, all nuclei with one proton are hydrogen, all nuclei with two protons are helium, and so on. However, the names of individual nuclides are often distinguished by their atomic mass number, which is the sum of the number of protons and neutrons in the nucleus. For example, the most common form of hydrogen is hydrogen 1, which has one proton and no neutrons in its nucleus. However, there are also isotopes of hydrogen with one or more neutrons, such as hydrogen 2, also known as deuterium, and hydrogen 3, also known as tritium. Similarly, the most common form of helium is helium 4, which has two protons and two neutrons in its nucleus. However, there are also isotopes of helium with different numbers of neutrons, such as helium 3 and helium 6. Other examples of nuclides include carbon-12, which has 6 protons and 6 neutrons in its nucleus, and uranium-235, which has 92 protons and 143 neutrons in its nucleus. Each nuclide has its own unique set of properties and behaviors, including stability, reactivity, and the ability to undergo radioactive decay. It is worth noting that some nuclides have multiple names or symbols, depending on the context. For example, carbon-14 is sometimes denoted as C14 or 14C, and uranium-235 is sometimes denoted as U-235 or 235U. Additionally, some nuclides may have different names or symbols in different languages or scientific disciplines. Nuclear species, also known as nuclides, have several characteristics and properties that are unique to their atomic structure. These properties are determined by the number of protons and neutrons in the nucleus, as well as the arrangement of electrons around the nucleus. Atomic number: the number of protons in the nucleus of an atom determines its atomic number and therefore, the element to which it belongs. This property is unique for each element and is essential for identifying the chemical properties of that element. Mass number: the total number of protons and neutrons in the nucleus of an atom is its mass number. Different isotopes of an element have the same atomic number but different mass numbers due to varying numbers of neutrons. Stability: the stability of a nucleus depends on its neutron-to-proton ratio. Nuclei with a high neutron-to-proton ratio are generally unstable and tend to undergo radioactive decay, while nuclei with a low neutron-to-proton ratio are more stable. Radioactivity: nuclides that are unstable may undergo radioactive decay, emitting particles such as alpha particles, beta particles, or gamma rays in the process. The rate of decay is determined by the half-life of the nuclide, which is the time it takes for half of the atoms in a sample to decay. Nuclear binding energy: the energy required to break apart a nucleus into its constituent protons and neutrons is called the nuclear binding energy. The amount of binding energy is related to the stability of the nucleus and is a crucial factor in nuclear reactions and energy generation. Isotopes. Isotopes are nuclides of the same element that have different numbers of neutrons. Different isotopes of an element may have different physical and chemical properties, and some isotopes may be unstable and undergo radioactive decay. Nuclear reactions. Nuclear reactions involve changes in the composition of atomic nuclei, such as the fusion of two nuclei or the splitting of a nucleus into smaller fragments. These reactions are accompanied by the release or absorption of energy and have important applications in energy generation, medical imaging, and other fields. In summary, nuclear species have a unique set of characteristics and properties that are determined by their atomic structure, including atomic number, mass number, stability, radioactivity, binding energy, isotopes, and nuclear reactions. These properties have important implications for the behavior and interactions of atomic nuclei, and have many practical applications in science and technology.